Look up at the night sky, and you'll see stars glittering like scattered diamonds, but there's something else hidden in the darkness between them. Vast clouds of cosmic dust and gas, so dense they blot out the light behind them, stretch across the galaxy like silent, shadowy giants. These are dark nebulae, some of the most mysterious structures in the universe. They don't glow like their brighter cousins, the emission or reflection nebulae. Instead, they absorb, conceal, and distort. They're cosmic riddles hiding secrets that defy our understanding, secrets that could rewrite what we know about star formation, the birth of planetary systems, and even the very fabric of space itself. What makes these cosmic shadows so fascinating isn't just what they obscure, but what they reveal when we study them closely. Some dark nebulae are stellar nurseries, cradling newborn stars within their inky folds. Others warp light in strange ways, bending the view of distant galaxies like funhouse mirrors. And then there are those that seem to defy physics, structures with shapes and movements that leave astronomers scratching their heads. They challenge our assumptions, forcing us to reconsider how matter behaves in the coldest, most isolated corners of the cosmos. That's exactly what we're diving into today. This isn't just a tour of space's hidden corners, it's a journey into the unknown. We'll explore 25 of the most puzzling dark nebulae ever discovered, each one raising questions that push science to its limits. Some of these cosmic enigmas might hold clues to the origins of life itself, while others could be hiding phenomena we haven't even imagined yet. So if you're ready to peer into the shadows where the universe keeps its deepest secrets, let's begin. Barnard 68 isn't just another patch of darkness in the cosmos, it's a ghostly void so dense it swallows starlight whole. Nestled in the constellation Ophiuchus, this molecular cloud lies a mere 500 light-years from Earth, close enough for astronomers to study in startling detail. But what makes it truly unsettling is the way it stares back at us, a perfect pitch-black circle against a sea of stars, like a cosmic pupil watching from the depths of space. The darkness isn't just an illusion. Barnard 68 is one of the coldest, most isolated places we've ever observed, with temperatures barely 10 degrees above absolute zero. Inside, molecules of hydrogen and helium squeeze together so tightly, not even the sharpest telescopes can pierce through. That's why some call it the black hole of the southern sky, not because it's a black hole, but because it shares that same eerie ability to vanish light without a trace. Yet this cloud hides more than just shadows. Within its frigid heart, gravity is quietly at work, compressing gas into knots that may one day ignite into new stars. It's a snapshot of deep time, a celestial cocoon caught in the act of becoming something else. And here's the strangest part, Barnard 68 isn't standing still. Precise measurements reveal it slowly rotating, a silent whirlpool in the dark. Scientists still can't agree why. Some argue it's the birth pangs of a future solar system, while others suspect unseen magnetic fields are twisting it into motion. What's certain is that Barnard 68 challenges our assumptions. Most dark nebulae are ragged, uneven things, but this one is unnervingly smooth, almost sculpted. Its edges are so sharply defined they look drawn by hand. That perfection raises eerie questions. Is there something inside shaping it? Or is this just how nature behaves when left undisturbed in the coldest corners of the galaxy? Whatever the answer, Barnard 68 reminds us that even the emptiest voids in space are anything but simple. The mystery of Barnard 68 doesn't end with its eerie symmetry. It's the center of a heated scientific debate that could reshape our understanding of how stars are born. On one side, researchers argue this dark nebula is a textbook example of a Bok globule, a type of isolated molecular cloud so dense it could collapse under its own gravity, eventually sparking new stars. But skeptics point out something odd. Barnard 68 seems too perfect, too undisturbed. Most star-forming regions are chaotic, turbulent places, yet this cloud's smooth edges and slow rotation suggest an almost serene environment. If it's truly on the verge of collapse, why isn't it showing the usual signs of stellar birth pangs? One compelling theory involves magnetic fields. Imagine invisible threads winding through the nebula, acting like cosmic scaffolding that holds the cloud together while quietly shaping its motion. These fields could explain why Barnard 68 rotates so uniformly, but here's the catch. To prove this, astronomers need to detect magnetic influences within a cloud so dark even light struggles to escape. It's like trying to map the veins of a shadow. Recent observations using polarized starlight around the nebula's edges hint at these hidden forces, but the full picture remains frustratingly out of reach. Then there's the timeline. If Barnard 68 is destined to form stars, how long would it take? Some models suggest it could take millions of years for gravity to finally overpower the cloud's internal pressure. Others propose a far more dramatic future, a sudden, violent collapse triggered by an external shockwave, perhaps from a nearby supernova. But with no neighboring stars to provide such a jolt, the nebula might just continue its slow, silent waltz through space indefinitely. What makes this cosmic puzzle even stranger is the absence of baby stars. Most dark nebulae this compact eventually reveal protostars' faint, warm glows buried deep within. Yet Barnard 68 shows no such signatures, as if it's resisting the inevitable. Could it be too cold, too pristine for star formation, or is there some unseen mechanism keeping it in stasis? Every answer only leads to new questions, and that's what makes this Inkai void so captivating. It's not just hiding starlight, it's guarding secrets about the delicate balance between chaos and creation in our universe. While Barnard 68 lurks in near-total isolation, the Coalsack Nebula makes an unmistakable splash across the southern sky, an Inkai blot so prominent it's visible to the naked eye. This sprawling dark cloud drapes itself over the constellation Crux, the Southern Cross, as if someone smudged the Milky Way with a thumbprint of cosmic soot. For centuries, it's been a celestial landmark, but not just for astronomers. Indigenous cultures across Australia and South America wove the Coalsack into their star lore long before telescopes turned toward it. The Wardaman people of northern Australia saw it as the head of a celestial emu, while the Mapuche of Chile called it the Great Llama, a dark guardian in their myths. Early European astronomers, though, met the Coalsack with confusion. In the 16th century, Portuguese explorer Amerigo Vespucci recorded it as a dark canopus, mistaking its silhouette for a faint star. Later, navigators relied on its stark contrast against the Milky Way to orient themselves in the uncharted southern seas. But the real puzzle was its nature. Unlike most nebulae known at the time, the Coalsack emitted no light. It wasn't until the 20th century that scientists confirmed it as a vast molecular cloud, a cold reservoir of dust and gas stretching 60 light-years wide, close enough that its tendrils blot out thousands of background stars. What makes the Coalsack especially fascinating is how it warps our view of the galaxy. Peer toward it, and you're staring through a keyhole of shadow, where the density of particles is so high, even infrared light struggles to pass. This isn't just an absence of stars, it's a celestial filter, subtly altering the color and brightness of distant starlight that dares to skim its edges. Modern telescopes reveal something even stranger. The nebula isn't uniformly dark. Some regions are nearly transparent, while others are so thick they could hide entire star clusters. Yet the Coalsack isn't just obscuring light, it's also a silent participant in the Milky Way's life cycle. Deep within its folds, radio telescopes have detected faint whispers of carbon monoxide, a telltale sign of molecules knitting themselves together in the cold. It's a slow-motion workshop where future stars might one day flicker to life, though for now, the nebula seems content to loom as a silhouette, a reminder that sometimes the most profound truths in astronomy come not from what shines, but from what hides in plain sight. Buried beneath the Coalsack's seemingly impenetrable veil, infrared telescopes have unveiled a secret. Stars are being born in the dark. While our eyes see only a void, instruments like the Spitzer Space Telescope and the James Webb see straight through the nebula's dust, revealing protostars flickering to life in pockets of collapsing gas. These aren't the bright, mature stars we're used to. They're embryonic suns still wrapped in thick cocoons of cosmic material, their light straining to escape. What's astonishing isn't just their existence, but their defiance of expectations. Conventional wisdom says stars need turbulence, collisions, and shockwaves to trigger their formation. Yet here, in one of the galaxy's most serene and isolated clouds, stars are emerging anyway, slowly, quietly, as if the universe is experimenting with a different recipe for creation. Take one of the Coalsack's most studied protostars, hidden deep in its western lobe. Dubbed the Dark Cradle by researchers, this object emits almost no visible light but glows fiercely in infrared, its heat betraying the violent process unfolding within. Gravity has carved a cavity in the surrounding dust, funneling material onto the growing star at speeds that would make a hurricane seem tame. But here's the twist: the Dark Cradle isn't alone. Scattered around it are smaller knots of infrared light, young stellar objects so faint they challenge the limits of detection. Some may never grow into full-fledged stars, stunted by the nebula's sparse resources. Others could be brown dwarfs, failed stars doomed to wander the cosmos in perpetual twilight. This raises a tantalizing question: how does star birth work in such a placid environment? Most stellar nurseries are chaotic places where supernova shockwaves or the winds of massive stars compress gas into star-forming clumps. The Coalsack, by contrast, is eerily calm. Without external triggers, its stars seem to form through sheer patience, gravity pulling molecules together over eons, undisturbed by the galaxy's usual violence. If that's true, it suggests a hidden population of slow-growing stars across the universe, overlooked because they don't fit the dramatic narratives we've come to expect. Even more puzzling are the filaments. High-resolution images show tendrils of dust winding through the Coalsack like cosmic rivers, connecting regions of star formation. These structures shouldn't survive long in the Milky Way's turbulent currents, yet they persist, hinting at unknown forces, perhaps magnetic fields or delicate pressure balances holding them together. Some astronomers speculate these filaments are the real architects of star birth here, guiding material inward like invisible highways. Others argue they're mere aftereffects, the scars of a process we don't yet understand. The Coalsack's biggest revelation might be humility. For centuries we saw it as a mere shadow. Now we know it's a workshop, one that operates by rules we're only beginning to decipher. Every new infrared image peels back another layer, showing us that even in the darkest corners of space, the universe is still writing its playbook. Slithering across the constellation Ophiuchus like a cosmic serpent frozen mid-strike, the Snake Nebula is one of the most striking dark clouds in our galaxy. Stretching nearly 30 light-years from end to end, its sinuous tendrils twist and coil through space with an eerie precision that seems almost deliberate. Through a telescope, it doesn't just look like a snake, it moves like one. The nebula's delicate filaments ripple subtly against the backdrop of the Milky Way, their edges frayed by invisible forces that have sculpted them over millennia. This isn't just a celestial Rorschach test. The Snake Nebula's structure holds vital clues about the hidden forces shaping our galaxy. Unlike the dense, compact Barnard 68, the Snake is wispy and elongated, a labyrinth of dust threads so thin they're nearly transparent at their edges. Yet despite this fragility, the nebula maintains its coiled shape, resisting the chaotic turbulence of interstellar space. The secret magnetism. Recent studies reveal the snake's filaments align eerily with the Milky Way's magnetic field, as if stitched into place by invisible cosmic threads. Here's where it gets fascinating. Interstellar magnetism is notoriously difficult to study. It's invisible to most telescopes, and its influence is often drowned out by more obvious forces like gravity or radiation. But the Snake Nebula acts like a giant cosmic compass. By mapping how its dust grains polarize starlight, astronomers have traced the magnetic field lines running through it, revealing a surprisingly orderly pattern. Some regions show fields so strong they've stretched the nebula into taut, nearly straight lines. Elsewhere, the fields twist like braids, hinting at collisions between different flows of interstellar material. The most puzzling feature, though, is the snake's scales. High-resolution images show tiny, overlapping knots of dust along its length, each one a miniature pressure point where magnetic forces may be pinching the cloud into segments. These knots could be the seeds of future star formation, except the snake shows no signs of stellar activity. It's too diffuse, too cold. Instead, it seems to exist in a fragile equilibrium, suspended between collapse and dissipation. What makes the Snake Nebula truly unique is its role as a laboratory. Unlike denser dark nebulae, its wispy structure lets astronomers observe magnetism's subtle effects in near-perfect isolation. Every twist in its filaments, every kink in its spine, tells a story about how invisible forces sculpt the galaxy's bones. And if researchers are right, this cosmic serpent might hold the key to understanding why some clouds birth stars, while others simply fade into the dark. The Snake Nebula's uncanny alignment with the Milky Way's magnetic field isn't just a curiosity, it's a direct challenge to how we think interstellar clouds evolve. For decades, the prevailing theory suggested turbulence was the primary sculptor of nebulae, with chaotic gas motions carving them into ragged, unpredictable shapes. But the snake's sinuous elegance defies that chaos. Its filaments aren't just drifting, they're practically dancing to the pull of invisible magnetic lines, a phenomenon that's forcing astronomers to rewrite the rules. Take the way the nebula resists fragmentation. In most turbulent models, clouds like the snake should have shattered into clumps long ago, their material scattered by interstellar winds. Yet here it lies, coiled and intact. The answer might lie in the magnetic field's surprising strength. Recent measurements suggest it's up to 10 times more powerful than expected for such a wispy structure. Imagine a spiderweb spun from steel, delicate to the eye but deceptively resilient. That's the snake. Its magnetic scaffolding could be acting as a cosmic skeleton, holding the nebula together against forces that ought to tear it apart. Then there's the question of origins. Where did these magnetic fields come from? One camp argues they're fossil relics, frozen into the nebula when it first condensed from the interstellar medium. If true, the snake could be a living archive, preserving the Milky Way's magnetic history in its folds. But rival studies propose a more dynamic picture: fields amplified by the cloud's own motion, like a dynamo generating electricity. As gas slides along the filaments, even slight twists could stretch and strengthen the magnetic lines, creating a feedback loop that shapes the nebula from within. The most tantalizing clue comes from the snake's knots. These dense pockets, strung along its length like beads, glow faintly in submillimeter wavelengths, revealing where magnetic pressure has squeezed gas to the breaking point. Normally, such knots would collapse into stars, but the snake's magnetic grip seems to be stalling that process. It's as if the nebula exists in a state of suspended animation, caught between the urge to fragment and the forces holding it together. Some researchers speculate this could be a new way for clouds to avoid star formation, a cosmic pause button we never knew existed. What's truly revolutionary is how the snake blurs the line between structure and force. We used to think of nebulae as passive clumps of gas, shaped by external shocks or gravity. Now we're seeing them as active participants, their very dust grains acting like tiny compass needles that align and reinforce the fields around them. It's a reminder that the universe's simplest shadows might be hiding the most sophisticated physics written not in light, but in the silent pull of magnetism. Lynn's dark nebula 1622 doesn't have the dramatic flare of Orion's glowing stellar nurseries, but what it lacks in brightness it makes up for in chemical intrigue. Tucked away in the constellation's shadowy outskirts, this unassuming cloud is a cosmic alchemist's lab, brewing molecules so rare they've rewritten our understanding of interstellar dust. Unlike the pristine hydrogen and helium found in most nebulae, this one's fingerprints reveal something startling: complex carbon chains, organic molecules, and even hints of prebiotic compounds, the kind that could one day seed life on distant worlds. The secret lies in its dust grains. While most dark nebulae act like simple light-blocking curtains, LDN 1622's particles are oddly efficient at sticking together, forming microscopic scaffolds where chemistry thrives. Radio telescopes have picked up signatures of cyanopolyine's long, carbon-rich molecules that shouldn't survive long in the harshness of space, yet here they are, clinging to dust like cosmic graffiti. Some scientists speculate the nebula's extreme cold, just a few degrees above absolute zero, acts as a protective freezer, slowing reactions that would destroy these fragile structures elsewhere. Others point to its isolation, shielded from ultraviolet radiation by thicker layers of dust. It's become a quiet refuge for chemistry too delicate for the galactic spotlight. Then there's the magnesium. Spectroscopic studies reveal an unexpected abundance of magnesium silicate grains, their crystalline structures far more ordered than the usual amorphous blobs found in similar clouds. These tiny cosmic snowflakes might hold clues to how stardust evolves. When blasted by shockwaves or ultraviolet light, most dust grains shatter or melt into featureless lumps. But LDN 1622's grains seem oddly resilient, their intricate shapes preserved like artifacts in a deep space museum. The real puzzle: this nebula shouldn't exist in its current form. At its estimated density, it ought to have collapsed under gravity long ago, either birthing stars or dispersing entirely. Instead, it lingers in stasis, a chemical factory frozen in time. Some researchers suspect magnetic fields, much like those in the Snake Nebula, are propping it up. Others argue its own dust is the stabilizer, with so many particles bumping together that they create a subtle pressure, balancing gravity's pull. What makes LDN 1622 extraordinary isn't just what it contains, but what it represents: a missing link between the raw materials of space and the building blocks of life. Most star-forming regions are too violent to preserve delicate chemistry. This quiet, unassuming shadow might be the universe's way of keeping its recipes safe until the conditions are just right. The Pipe Nebula cuts a dramatic figure against the star-drenched backdrop of Sagittarius, a celestial silhouette so uncanny, it looks like a smoker's pipe sketched across the heavens. Stretching over 7 degrees of sky, that's 14 full moons lined up end to end. Its stem and bowl are unmistakable even to the naked eye under dark skies. But this isn't just a cosmic coincidence. The pipe is a window into the scaffolding of our galaxy, part of a vast network of dust clouds that trace the Milky Way's spiral arms like ink blots on a star map. What makes the Pipe Nebula special isn't just its shape, but its transparency. Unlike denser dark nebulae that swallow light entirely, the pipe's dust is just thick enough to dim the stars behind it, creating a gradient of shadows that reveals its three-dimensional structure. Astronomers call this differential extinction, a fancy term for how starlight filters through the cloud's varying layers, allowing scientists to reconstruct its depth and density with surprising precision. By measuring how much the pipe dims stars of known brightness, they've mapped its contours in detail, uncovering a complex topography of ridges and valleys in interstellar space. The real revelation, though, is the pipe's place in a much larger puzzle. It's just one segment of the Dark Horse Nebula, an enormous serpentine complex winding through Sagittarius and Ophiuchus. Together, these clouds form a celestial tape measure, helping astronomers gauge distances across our galactic neighborhood. Here's how it works. The pipe's position, combined with its dust composition, acts as a signpost in the Milky Way's disk. By studying how its shadow falls on background stars, some near, some far, researchers can triangulate the nebula's distance, about 600 light-years, and use it as a reference point to chart the galaxy's structure beyond. But the pipe isn't just a passive ruler. Its dust grains hold clues to the raw materials of star formation. Spectroscopic studies show they're richer in silicates and carbon compounds than typical interstellar dust, suggesting they've been chemically altered by eons of exposure to cosmic rays and stellar winds. Some grains even resemble microscopic fluff balls, their porous structures ideal for trapping water, ice, and organic molecules. This raises a tantalizing possibility. The same dust that now blocks our view might one day become the building blocks of planets or even life around newborn stars. Yet the Pipe Nebula's most enduring mystery is its stillness. Unlike the Coalsack or Snake Nebula, it shows no signs of active star birth. No protostars flicker in its depths. No infrared glows betray collapsing gas. It's as if this cloud is waiting, its dust suspended in a cosmic pause. Some theories suggest it's too diffused to collapse, its particles held apart by subtle magnetic fields or turbulent motions. Others propose it's simply young, a recent arrival in the galactic cycle that hasn't yet felt gravity's pull. Whatever the reason, the pipe serves as a reminder, not all shadows in space are nurseries. Some are archives preserving the quiet moments before creation begins. Standing at the intersection of art and science, the Pipe Nebula does more than captivate stargazers. It's a tool, a time capsule, and a testament to the hidden structures shaping our galactic home. Every time we trace its smoky outline against the Milky Way, we're not just seeing a cloud, we're reading a map of the universe's hidden architecture, written in dust and starlight. The Pipe Nebula isn't just a striking silhouette. It's a celestial landmark, one of the few dark clouds massive enough to help us map the Milky Way's hidden architecture. Like following a trail of breadcrumbs, astronomers use its position and structure to trace the contours of our galaxy's nearest spiral arm, the Sagittarius arm. But here's the twist: the pipe's role as a cosmic signpost comes with a catch. Despite decades of study, its exact distance from Earth remains hotly contested, with estimates swinging between 400 and 700 light-years. That uncertainty isn't just a technicality, it's a window into the challenges of measuring space's darkest voids. To understand why the pipe matters, picture the Milky Way as a vast, swirling disk. From our vantage point inside it, spiral arms appear smeared across the sky, their stars and gas clouds overlapping in a blur. Dark nebulae like the pipe cut through that chaos, their dense dust blocking light in predictable ways. By analyzing how the pipe dims thousands of background stars, each at a known brightness, scientists can triangulate its location in three-dimensional space. It's akin to holding up a finger to block distant streetlights. The angle of your finger reveals whether the light is near or far, yet the pipe resists easy answers. Some studies, relying on star-counting techniques, place it closer to us, nestled just beyond the Scorpius-Centaurus Association, a nearby stellar nursery. Others, using infrared spectroscopy to peer through its dust, argue it's farther out, possibly part of a denser branch of the Sagittarius arm. The discrepancy highlights a fundamental problem. Dark nebulae don't emit their own light, so traditional distance measuring tools falter. Even the Gaia spacecraft, which has mapped over 1 billion stars with stunning precision, struggles to pin down the pipe's position because its dust obscures the very stars needed for calibration. The debate takes a fascinating turn when we consider the pipe's shadow effect. As the nebula drifts through space, its dust subtly reddens the light of stars lying beyond it like a cosmic filter. By measuring this reddening across different wavelengths, astronomers can estimate not just distance, but the nebula's dust composition and grain size. Recent data suggests the pipe's grains are unusually large for its location, a clue it might be older than its neighbors, its particles clumped together over eons. If true, it could mean the pipe is a relic of an earlier galactic epoch, a surviving fragment of the Milky Way's building blocks. What's at stake isn't just a number on a chart. The pipe's distance ties directly to our understanding of the Sagittarius arm's structure. If it's closer, the arm may be narrower and more loosely wound than models predict. If it's farther, it could imply the presence of a previously unnoticed spur, a kink in the galactic spiral. Either way, the pipe forces us to confront an humbling truth. Even in our own cosmic backyard, the simplest shadows can defy measurement. And that uncertainty, ironically, makes it one of astronomy's most valuable tools. Every time we fail to pin it down, we learn something new about the galaxy's hidden geometry. So while the pipe's distance remains elusive, its legacy is clear. It's a reminder that darkness isn't just the absence of light. It's a canvas for discovery, a place where the universe writes its secrets in dust and shadow. And as long as it keeps those secrets just out of reach, astronomers will keep looking, because sometimes the most profound truths lie not in what we see, but in what we're still striving to measure. The dark Doodad might sound like a cosmic joke, but this whimsically named nebula in the constellation Musca is anything but frivolous. Stretching like a celestial brushstroke across the southern sky, it's one of the most striking examples of a starless dark cloud, a dense filament of gas and dust that stubbornly refuses to form stars despite its apparent readiness. At nearly 30 light-years long and just a few light-years wide, its needle-like silhouette stands out sharply against the Milky Way's glow, as if someone dragged a charcoal line through a field of diamonds. What makes the dark Doodad so fascinating isn't just its shape, but its defiance. Most dark nebulae, this dense eventually fragment under gravity's pull, collapsing into knots that ignite as protostars. Yet here, the Doodad lingers in a state of eerie stillness. Radio telescopes detect no telltale whispers of collapsing gas, no infrared glows hinting at hidden stellar embryos. It's a cosmic pause button frozen in time. The question is why? One clue lies in its environment. Unlike star-forming powerhouses like Orion, the dark Doodad drifts through a relatively quiet corner of the galaxy, far from the shockwaves of supernova or the fierce winds of massive stars. Without these external triggers, its gas may simply lack the push needed to tip over the edge into collapse. But isolation isn't the whole story. Spectroscopic studies reveal another twist. The Doodad's dust grains are unusually fluffy, their porous structures acting like microscopic shock absorbers. When gravity tries to compress the cloud, these grains might cushion the blow, dissipating energy that would otherwise spark star birth. Then there's the magnetism. Recent polarization measurements show the Doodad's filaments align neatly with the Milky Way's magnetic field, suggesting invisible forces are propping it up like cosmic scaffolding. This could explain its remarkable coherence over such an immense length. While most clouds fray into clumps, the Doodad's magnetic threads might be knitting it together, resisting gravity's tug like a tightrope walker balancing on a galactic scale. Yet the biggest mystery is its age. Dark nebulae typically live fast and die young, either crumbling into stars or dispersing within a few million years. The Doodad, however, shows signs of extreme longevity. Its chemical composition hints at a history stretching back tens of millions of years. How has it avoided the fate of its more dramatic cousins? Some theorists propose it's a relic cloud, a surviving fragment of an older, larger structure that's been slowly eroded by time. Others wonder if it's caught in a delicate equilibrium, its internal turbulence perfectly offsetting gravity's pull. The dark Doodad's true significance might lie in what it teaches us about the galaxy's quiet majority. While astronomers often focus on the fireworks of star formation, most interstellar clouds lead far less eventful lives. They drift, they persist, and they fade silent witnesses to the universe's slower rhythms. By studying this cosmic oddity, we're not just unraveling the secrets of dark nebulae, we're learning to appreciate the beauty of stillness in a cosmos obsessed with chaos. Nestled in the constellation Cygnus like a drop of spilled ink on a starry canvas, the Ink Spot Nebula is a study in extremes. While its flashy neighbor, the North American Nebula, dazzles with glowing gas and newborn stars, this unassuming dark cloud huddles in the cosmic background so dense it devours nearly all light that dares to pass through. At just a few light years across, it's small by nebula standards, but what it lacks in size, it makes up for in sheer opacity. Peer through a telescope and the contrast is startling. Where the North American Nebula blazes with pinks and reds, the ink spot hangs beside it like a void punched through reality, its edges so sharply defined they seem almost artificial. The secret to this nebula's darkness lies in its dust, not just the amount, but the peculiar way it's arranged. Most dark nebulae scatter their particles unevenly, creating patchy shadows. The ink spot, however, boasts dust grains packed so tightly they form what astronomers call a uniform extinction layer. Imagine a cosmic sandstorm where every grain lines up perfectly, blocking light with military precision. Spectroscopy reveals why. These aren't your typical interstellar dust motes. They're rich in complex carbon compounds, their surfaces layered with microscopic ices and organic molecules that absorb light far more efficiently than simpler silicates. It's as if someone filtered the galaxy's dust through a sieve, leaving only the darkest, most light-hungry particles behind. How did such a dense pocket form? One theory points to a cosmic traffic jam. The ink spot sits at the crossroads of multiple gas flows in the Cygnus region, where colliding streams of interstellar material may have piled up like snowdrifts in a windstorm. Another idea involves an ancient stellar explosion. A long-vanished supernova could have compressed the surrounding dust, leaving behind this tightly packed remnant. But the most tantalizing possibility involves magnetism. Recent polarization studies hint at strong magnetic fields threading through the nebula, their invisible lines acting like cosmic comb, aligning the dust grains into a light-blocking phalanx. What truly baffles scientists, though, is the ink spot silence. Clouds this dense usually hum with the radio signatures of collapsing gas or the infrared whispers of hidden protostars. Yet here, the nebula offers only eerie quiet. It's possible we're witnessing a rare cosmic moment, a dark nebula caught just before star formation begins, its materials poised on the knife's edge between stability and collapse. Or perhaps the ink spot is something rarer still, a dark nebula that's found a way to resist gravity's pull indefinitely, its dust locked in a perfect balance of forces we don't yet understand. Standing in the shadow of its radiant neighbor, the Ink Spot Nebula serves as a reminder that darkness isn't merely the absence of light. It's a phenomenon with its own mysteries, its own rules. While the North American Nebula shouts its brilliance across the cosmos, this Inkai blot whispers puzzles that may rewrite how we think about the galaxy's hidden architecture. Every photon it swallows carries a story we're only beginning to decode. Lupus 3 isn't just another dark nebula, it's a cosmic tug of war between shadow and light. Located about 500 light-years away in the constellation Lupus, this turbulent cloud is a stellar nursery in action, where newborn stars blaze through the very dust that birthed them, carving glowing cavities into the darkness. Through telescopes, the scene is nothing short of dramatic. Tendrils of Inkai dust twist around luminous young stars, their fierce radiation eroding the nebula like sunlight burning off morning fog. Yet curiously, not all of Lupus 3 surrenders to the light. While some regions wither under the star's glare, others cling stubbornly to their darkness, resisting illumination in ways that defy simple explanation. At the heart of this mystery lies a delicate balance, one that starts with the nebula's unusual structure. Unlike the uniform clouds we've seen so far, Lupus 3 is a patchwork of dense cores and wispy filaments. Its darkest pockets are starless cores, knots of gas so thick even the intense radiation from nearby stars can't penetrate them. Imagine holding a flashlight to a snowbank. The surface might melt, but deep inside, the ice remains untouched. That's precisely what's happening here. These cores are shielded by their own sheer density, their outer layers absorbing and scattering the incoming starlight before it reaches the interior. But density alone doesn't explain everything. Lupus 3's resistant dark zones also thrive because of their chemistry. Spectroscopic studies reveal an abundance of complex molecules, carbon monoxide, ammonia, and even organic compounds coating the dust grains like microscopic armor. These molecules don't just block light, they absorb specific wavelengths, converting the star's energy into subtle heat that helps stabilize the cores against disruption. It's a cosmic feedback loop. The more radiation the nebula faces, the more its chemistry adapts to preserve its darkest sanctuaries. Then there's the role of magnetism. Recent observations show Lupus 3's most persistent dark regions align with powerful magnetic field lines, their dust grains stretched into elongated shapes that channel radiation away like a prism splitting light. In essence, these pockets aren't just passively resisting the stars, they are actively deflecting their influence. The result is a nebula caught in a dynamic stalemate, where pockets of pristine darkness survive mere light years away from stellar infernos. What makes Lupus 3 truly remarkable is the window it offers into star formation's earliest stages. Those defiant dark cores aren't just holdouts, they're likely the next generation of stellar nurseries, biding their time until gravity tips the scales. Some may already harbor failed stars, brown dwarfs too small to ignite fully, while others could be incubating planetary systems we'll never see directly. For astronomers, this mosaic of light and shadow is a living laboratory, demonstrating how chaos and order coexist in the slow-motion dance of cosmic creation. The lesson of Lupus 3 is clear. Darkness in the universe isn't just emptiness waiting to be filled. It's a force in its own right, shaping and being shaped by the very stars that seek to destroy it. Every patch of unyielding shadow here whispers secrets about resilience, about the unseen battles between radiation and gravity, and ultimately about how even the brightest corners of the cosmos depend on the dark. Lupus 3 doesn't just resist nearby starlight, it rewrites the playbook on how molecular clouds interact with radiation. Conventional wisdom suggests that when young, energetic stars ignite within or near a dark nebula, their fierce ultraviolet rays should tear through the surrounding gas, ionizing it into glowing streamers and hollowing out cavities. Yet here, dense pockets of Lupus 3 stand their ground, cloaked in shadows that refuse to dissipate. This defiance isn't random, it's a calculated survival tactic, one that hinges on the nebula's unique anatomy and chemistry. Take the cloud's dark cores, regions so dense they act like cosmic bunkers. While most of the nebula's outer layers erode under stellar winds, these knots of gas and dust maintain their integrity through sheer mass. Picture a sandstorm raging against a stone wall. The lighter grains scatter, but the heaviest boulders barely budge. Inside these cores, the column density of material is so high, incoming photons get absorbed or deflected before they can break molecules apart. It's a self-shielding mechanism where the cloud's own bulk becomes its best defense. But mass alone doesn't explain the full picture. Spectroscopy reveals another layer of protection. Complex organic molecules like polycyclic aromatic hydrocarbons PAH clinging to dust grains like microscopic armor. These aren't passive bystanders, they're active participants in the nebula's resistance. When starlight hits a PAH, the energy doesn't tear the cloud apart. Instead, it gets converted into subtle vibrations, dissipating harmlessly as heat. It's the cosmic equivalent of a bulletproof vest, absorbing and dispersing impact energy. Even more intriguing is the role of turbulence. While we often think of chaos as destructive, Lupus 3's internal gas motions might be its saving grace. High-resolution radio maps show the nebula's material isn't sitting still, it's churning, with supersonic flows creating a dynamic buffer against radiation. As stars blast the cloud with energy, these chaotic motions scatter the incoming radiation, preventing it from focusing on any single region long enough to do irreversible damage. Think of it like trying to light a candle in a hurricane. The flame never gets a chance to take hold. The implications stretch far beyond this one nebula. If dark clouds can naturally shield themselves from ionizing radiation, it means stellar feedback. The process by which stars regulate their own birth might be less efficient than we thought. Galactic models often assume young stars quickly clear their nurseries, shutting down further star formation. But Lupus 3 suggests some clouds could delay that reckoning, nurturing multiple generations of stars in the same cradle. Perhaps the most tantalizing possibility is what these resilient cores are hiding. Shielded from destructive radiation, their interiors could be preserving pristine chemical conditions, the kind that might foster probiotic molecules or even the building blocks of life. While the outer layers of Lupus 3 battle the stars, its darkest heart might be quietly assembling the ingredients for something far greater. In that way, this nebula isn't just challenging our assumptions about astrophysics. It's hinting at how cosmic shadows might cradle the seeds of life itself. Stretching across the constellation Cygnus like a jagged scar through the Milky Way, the Cygnus Rift isn't just a dark nebula, it's an optical illusion on a galactic scale. From our vantage point on Earth, this vast complex of dust clouds appears to slice the galaxy in two, as if some cosmic hand drew a chalk line through its brightest star fields. But the rift isn't a true divide. It's a foreground curtain, a chance alignment of dense molecular material just 500 light-years away that happens to block our view of the galaxy's glittering core beyond. Peer toward Cygnus on a clear summer night, and you'll notice something unsettling. The Milky Way's usual river of starlight seems to fray and dim, its central bulge obscured by what ancient astronomers called the northern Coalsack. Early star charts from Persia to China marked this region with unease, interpreting its darkness as a celestial gate, a river of souls, or even the scorched aftermath of a dragon's breath. The Navajo saw it as the black god's blanket, a shroud woven from cosmic ashes. These myths weren't entirely wrong. The Cygnus Rift does veil something monumental. Behind its dust lies the gateway to the Milky Way's heart, a realm so packed with stars that their combined light would outshine the full moon if not for this interstellar smokescreen. Modern astronomy reveals the rift's true nature, not a void but a sprawling tapestry of star-forming filaments. Radio telescopes have mapped its structure in detail, uncovering tendrils of cold gas laced with complex organic molecules. Some regions, like the Inkai Nebula LDN 988, are so thick with carbon-rich dust that they absorb 99% of visible light. Others appear translucent, their particles just sparse enough to tint distant starlight crimson, a phenomenon called interstellar reddening that helps astronomers gauge the rift's composition. What makes the Cygnus Rift extraordinary is how it distorts our cosmic perspective. By blocking our view of the galaxy's core, it creates the illusion that we're peering into an abyss when in reality we're staring through a keyhole. Infrared telescopes like Spitzer and Webb pierce this veil, revealing thousands of hidden stars whose light has been scrambled by the rift's dust into eerie, diffraction-spiked apparitions. These observations unveil a paradoxical truth. The darker the nebula appears, the more it teems with invisible activity. Submillimeter scans detect protostars buried deep within its folds, their faint heat signatures betraying nurseries where future solar systems take shape. Yet the rift's greatest scientific gift might be its role as a cosmic filter. As starlight passes through its dust, specific wavelengths get absorbed, leaving behind chemical fingerprints that tell us what these clouds are made of. Surprisingly, the Cygnus Rift contains more than just simple silicates. Its grains are studded with frozen water, methane, and even precursors to amino acids. Some researchers speculate that when these particles eventually collide in protoplanetary disks, they could deliver the raw ingredients for life to newborn worlds. Culturally and scientifically, the Cygnus Rift forces us to reckon with the limits of human vision. For millennia, we interpreted its shadows as emptiness. Now we know it's a lens, one that twists our view of the galaxy while hiding revelations about how stars, planets, and perhaps even life itself begin. The darkness isn't an endpoint, it's a doorway, and every photon that fails to reach our eyes carries a story about what lies beyond. The Taurus molecular cloud doesn't just drift through space, it looms over us, a celestial neighbor so close we could almost touch it. At just 450 light-years away, this sprawling complex of gas and dust is the closest major star-forming region to Earth, offering astronomers a front-row seat to the birth of stars. Yet what makes Taurus truly captivating aren't its glowing infant stars, but the shadows between them, dense ink-black patches like Barnard 211, where the next generation of suns is quietly taking shape under a veil of cosmic dust. These dark pockets are far from empty. They're pre-stellar cores, knots of gas so cold and dense they teeter on the edge of collapse. In most nebulae, such regions would be hidden behind layers of obscuring material, but Taurus's proximity pulls back the curtain. Radio telescopes like ALMA have mapped these cores in stunning detail, revealing intricate structures where gravity's grip is slowly overcoming pressure and turbulence. Some resemble cosmic eggs, near-perfect spheres of gas with masses up to 30 times that of our Sun. Their interiors so still and cold that molecules like nitrogen and carbon monoxide freeze onto dust grains, forming icy mantles. These ices aren't just frost, they're the raw materials for future planetary systems, a chemist's stockpile waiting for the spark of starlight to set them in motion. What's astonishing is how quiet these nurseries are. Unlike the fireworks of Orion's star factories, Taurus's dark cores evolve with almost meditative slowness. Take Barnard 211, a textbook example of a starless core. Despite its density, enough material to form several sun-like stars, it shows no signs of fragmentation or collapse. Magnetic fields thread through it like invisible stitches, holding it together against gravity's pull. Submillimeter observations reveal something even stranger. The core's outer layers are gently contracting while its heart remains eerily still, as if the nebula is holding its breath. This isn't stagnation, it's suspense. Taurus's dark cores represent the universe in its most patient mood, where star formation unfolds over millions of years rather than millennia. By studying their chemistry, astronomers have uncovered clues about how solar systems begin. The ices coating these dust grains contain water, methanol, and even simple sugars, molecules that, when heated by a newborn star, could jumpstart the formation of comets, asteroids, and perhaps the building blocks of life. Yet Taurus has another secret. Not all its dark patches will ignite. Some cores are destined to fade, their material dispersing back into the interstellar medium. Others might birth brown dwarfs, failed stars too small to shine. This duality makes the cloud a cosmic laboratory, showing us that darkness isn't just the prelude to light, it's a story with multiple endings. Every observation peels back another layer, revealing how the faintest whispers of gravity and chemistry shape the universe's grandest designs. Standing in the shadow of Taurus, we're reminded that some of the universe's most profound transformations happen in silence, hidden behind curtains of dust. These dark nebulae aren't just obscuring the stars, they're guarding the delicate processes that make them possible. And thanks to Taurus's unprecedented proximity, we're privileged to watch this cosmic drama unfold, one fragile core at a time. Taurus's quietest cores are cosmic enigmas wrapped in cold regions so still and undisturbed, they defy our expectations of how stars should form. At temperatures barely 10 degrees above absolute zero, these dense pockets of gas drift through the nebula like hibernating giants, their interiors untouched by the chaotic turbulence that typically sparks stellar ignition. What makes them extraordinary isn't just their frigid state, but the questions they raise. If gravity alone governed star birth, these cores should have collapsed long ago. Yet they linger, suspended in a state of perfect hesitation, as if waiting for some unseen signal. The mystery deepens when we peer inside. Advanced radio telescopes have mapped the internal structure of cores like Barnard 213, revealing layers of gas so finely balanced they resemble a nesting doll of pressures. At the outermost edges, gentle supersonic flows ripple through the material remnants of the cloud's turbulent past, but venture deeper and the motion stills. The heart of these cores is preternaturally calm, with gas densities high enough to form stars, yet no telltale clumps or contractions betray impending collapse. It's as if someone pressed pause on the universe's clock. One explanation lies in the delicate interplay between gravity and magnetic fields. In most star-forming regions, gravity eventually overpowers the resisting forces, pulling material inward until fusion ignites. But Taurus's silent cores seem to exist in a golden zone. Their magnetic fields are just strong enough to counteract gravity's pull, creating a cosmic standoff. Imagine a balloon inflated to its limit, where the outward push of air matches the rubber's tension. These cores hover in that equilibrium, their magnetic skin holding back collapse with exquisite precision. Yet magnetism doesn't act alone. Chemistry plays a surprising role. The dust grains here are coated in exotic ices, carbon monoxide, formaldehyde, and even cyanide compounds that act like microscopic shock absorbers. When gas particles collide, these icy mantles convert kinetic energy into subtle vibrations, dissipating the heat that might otherwise trigger localized collapse. It's a phenomenon akin to walking on quicksand. The faster you struggle, the more you sink. In Taurus, the core's own chemistry may be preventing them from struggling at all. The most tantalizing possibility: these silent cores could be evidence of a slower, gentler path to star formation, one where turbulence and shockwaves aren't the primary midwives. Instead, quiet accumulation might dominate, with cores growing denser over millennia until they reach a critical threshold. Some models suggest external triggers, a passing shockwave from a distant supernova or the gravitational nudge of a nearby star, could break the deadlock. But until that happens, these patches of darkness remain cosmic time capsules, preserving the conditions of the interstellar medium as it existed before light intervened. What they're hiding could rewrite our understanding of stellar beginnings. Hidden beneath their icy veils, molecules essential for planetary formation, water, methane, and even simple amino acids may lie in wait, undisturbed by radiation or heat. It's a reminder that darkness isn't just the absence of light. It's a sanctuary where the universe's most delicate recipes simmer unseen. And in Taurus, we're granted a rare privilege, watching the ingredients assemble before the oven even turns on. The Horsehead Nebula may be astronomy's most famous silhouette, a celestial smokestack rearing against Orion's glowing backdrop, but its dramatic pose owes everything to the unsung dark nebulae surrounding it. While our eyes instinctively focus on that iconic equine profile, the real story unfolds in the shadows behind and beside it, where lesser-known clouds like LDN 1631 and Barnard 33 weave a complex tapestry of darkness. These aren't just supporting actors, they're master sculptors, their tendrils of cold dust carving the voids that make the Horsehead stand out so vividly against the starscape. Zoom out from the Horsehead's familiar neck, and you'll notice something startling. The same dense molecular cloud that forms its silhouette continues far beyond, stretching like an ink-eye stain across Orion's belt. LDN 1631, a sprawling dark nebula just south of the Horsehead, shares its composition of hydrocarbon-rich dust but behaves entirely differently. Where the Horsehead's edge is sharply eroded by radiation from the nearby star Sigma Orionis, LDN 1631's borders appear feathery and diffuse, its outermost dust particles slowly boiling away into space. This contrast reveals a hidden truth. The Horsehead isn't a standalone structure but the most photogenic fragment of a much larger dynamic system. Radio observations uncover even more surprises. While the Horsehead's famous prow points toward Earth, creating that perfect profile, neighboring Barnard 33 curves away from us in 3 dimensions, a funnel-shaped void where magnetic fields have corralled dust into spiraling filaments. These twisted strands, invisible in optical light, glow faintly in submillimeter wavelengths, tracing the paths of interstellar gas as it's drawn toward regions of future star formation. Some filaments stretch over 15 light-years, connecting the Horsehead to other dark nebulae like cosmic umbilical cords. The real magic happens where these clouds meet the light. The Horsehead's dramatic contrast comes not just from its own density, but from the glowing emission nebula IC4034 right behind it, a backdrop ignited by massive young stars. Here, physics becomes artistry. Ultraviolet radiation strips electrons from hydrogen atoms, making the gas fluoresce pink, while the dark nebulae in front selectively block that glow. The effect resembles a stained glass window, where darkness and brilliance collaborate to create celestial iconography. Yet the surrounding dark nebulae guard secrets the Horsehead never could. Deep within their coldest recesses, astronomers have discovered bizarre carbon chain molecules and organic compounds that shouldn't survive Orion's intense radiation field. Somehow, these clouds have developed protective pockets, natural bunkers, where delicate chemistry persists against all odds. It's a reminder that while we marvel at the Horsehead's beauty, its overlooked neighbors might hold the keys to understanding how complex molecules, the precursors to life, endure in even the harshest cosmic environments. Together, these shadowy clouds form a dynamic ecosystem far richer than any single silhouette. The Horsehead is merely the brightest star in this dark constellation, a gateway to understanding how light and shadow collaborate to shape our view of the universe. Every time we admire its profile, we're really witnessing a grand interplay of forces, where the unseen darkness writes half the story in dust and magnetic fields. The Cone Nebula's jagged peak might steal the spotlight, but its shadowy base is where the real cosmic drama unfolds. While the nebula's iconic tip glows with the reflected light of young stars, the dense, dark foundation below remains eerily untouched, a fortress of dust and gas so thick it defies the violent stellar winds tearing at its edges. Nestled in the constellation Monoceros, this region isn't just hiding from the light. It's actively resisting it, creating a stark boundary between chaos and calm that challenges our understanding of how nebulae evolve. At first glance, the cone's base looks like a simple wall of darkness, but radio telescopes reveal a far more intricate structure, a layered defense system against the radiation pouring in from nearby massive stars. The outermost filaments are frayed and ionized, their atoms stripped bare by ultraviolet bombardment. Yet just a light year deeper, the nebula's density spikes dramatically, forming a near-impenetrable barrier where dust grains stack like bricks in a cosmic dam. These particles aren't just passively blocking light, they're absorbing and scattering it, converting the energy of incoming photons into subtle heat that radiates away harmlessly. It's a celestial insulation job so effective, the innermost regions of the base remain colder than the void of space itself. What's truly remarkable is how this darkness thrives in one of the galaxy's most hostile neighborhoods. The Cone Nebula sits within the turbulent Monoceros OB1 association, a stellar nursery where massive stars blast their surroundings with enough radiation to evaporate lesser clouds within millennia. Yet the base endures, its resilience tied to a delicate balance of forces. Magnetic fields thread through its depths like reinforcing rods, binding the dust into cohesive strands that resist erosion. Meanwhile, the sheer weight of accumulated material equivalent to thousands of solar masses creates a gravitational anchor, preventing the cloud from being blown apart like its more exposed neighbors. The base's secret weapon might be chemistry. Spectroscopy uncovers a rich inventory of complex molecules here, from carbon chains to icy water mantles coating the dust grains. These compounds act like a cosmic ablative armor, sacrificing themselves to absorb destructive energy while preserving the cloud's core. Some regions show signs of freeze-out, where gases like carbon monoxide have condensed onto dust particles, further increasing the nebula's opacity. It's a self-reinforcing cycle. The darker the base becomes, the better it shields itself, allowing even more material to accumulate in its depths. Yet the most tantalizing mystery lies in what this darkness protects. While the cone's tip blazes with newborn stars, its base shows only faint infrared flickers, hints of protostars so deeply embedded, their light may not escape for millions of years. These embryonic suns are growing in near-total isolation, shielded from the very radiation that typically triggers star formation. If they eventually emerge, their planetary systems could be radically different from those born in brighter environments, rich with the complex organics preserved by the nebula's shadows. The Cone Nebula's base isn't just a passive shield, it's a testament to darkness as an active, dynamic force. In a universe that often equates brilliance with importance, this Inkai stronghold reminds us that some of the most profound transformations happen unseen, where the absence of light isn't an ending, but a beginning. The Great Rift in Aquila isn't just a dark nebula, it's a cosmic blind spot, a sprawling curtain of dust that complicates our view of the Milky Way's most crowded regions. Stretching across the constellation Aquila like a slash through a star map, this dense band of interstellar material blocks our line of sight to the galaxy's core, obscuring thousands of stars and forcing astronomers to piece together the hidden structure behind it. From Earth, the effect is dramatic. Where the Milky Way typically dazzles with countless points of light, the Great Rift interrupts with an abrupt, starless gash, as if someone erased a section of the night sky. What makes this dark nebula uniquely frustrating and fascinating is how it distorts our galactic senses. Modern surveys like Gaia have mapped over 1 billion stars with precision, but the Great Rift's dust acts like a celestial fog, dimming and reddening the light of everything behind it. Stars that should shine brightly at visible wavelengths become faint ghosts or vanish entirely, creating artificial voids in our data. It's not just an observational nuisance. This obscuration skews our understanding of the Milky Way's spiral arms, making distances and densities harder to calculate. To peer through the rift, astronomers must rely on workarounds, infrared and radio telescopes that detect heat signatures and molecular emissions invisible to optical instruments. Yet the Great Rift's dust isn't uniformly oppressive. Like a fading ink blot, its density varies, offering tantalizing glimpses of what lies beyond. In some regions, the veil is thin enough to reveal background stars tinted deep crimson, their light filtered through countless microscopic grains. These reddened stars serve as cosmic probes, their altered colors betraying the composition and thickness of the dust they've passed through. By studying these subtle shifts, researchers have reconstructed the rift's three-dimensional structure, revealing it as a complex network of filaments rather than a solid wall. Some strands stretch hundreds of light years, weaving through space like dark rivers. The most surprising discovery: this isn't a static structure. The Great Rift's dust clouds are in motion, drifting at speeds of several kilometers per second. Radio observations of molecules like carbon monoxide trace these currents, showing how turbulence from nearby stellar winds and supernova remnants stirs the nebula into swirling eddies. These dynamics make the rift a living laboratory for studying how interstellar material evolves under external forces. In some areas, the dust is collapsing into pre-stellar cores. In others, it's being blown apart, its particles scattered back into the galactic medium. For all its challenges, the Great Rift holds an unexpected gift. It's one of the best places to study cosmic dust itself. Unlike brighter nebulae where radiation alters dust chemistry, the Rift's sheltered environment preserves pristine particles, some dating back to the galaxy's early epochs. Spectroscopic studies reveal a surprising diversity grains of silicate, graphite, and even organic compounds like polycyclic aromatic hydrocarbons. These tiny fragments are more than just obstructions. They're the raw materials for future stars and planets, and their properties influence everything from star formation rates to the birth of planetary atmospheres. The Great Rift's ultimate lesson might be about perspective. For centuries, humanity saw its darkness as emptiness. Now we recognize it as a lens, one that reshapes our view of the galaxy while hiding revelations about its structure and history. Every photon that fails to reach us carries a story, and every gap in our star maps hints at the universe's hidden complexity. In that sense, the Rift isn't just obscuring the Milky Way, it's inviting us to explore it in wavelengths beyond the light our eyes can see. The Dark Tower in Scorpius isn't just another shadow in the cosmos. It's a monolith of dust, a skyscraper of cosmic debris that looms over the star-flecked backdrop of the Milky Way like a sentinel guarding the galaxy's secrets. Rising nearly 50 light-years from base to tip, this colossal pillar stands in stark contrast to the radiant nebulae that flank it, their glowing gases painting the surrounding space in hues of pink and gold. While those luminous clouds announce their presence with brilliance, the Dark Tower commands attention through absence, its inky silhouette carving a void where starlight dares not tread. What makes this structure so arresting isn't just its scale, but its defiance. Unlike many dark nebulae that fray at the edges under stellar winds, the tower's outline remains razor-sharp, its flanks sculpted by radiation from nearby massive stars. These celestial blowtorches, some shining with the intensity of 100 suns, should have evaporated the tower's dust long ago. Yet here it stands, its base anchored in a sea of turbulence, its peak stretching toward the void like a challenge. The secret to its endurance might lie in its sheer density. Radio observations reveal a core so packed with carbon-rich grains and frozen molecules that even the fiercest ultraviolet light struggles to penetrate. It's less a cloud and more a fortress, its walls layered like armor against the onslaught. But the tower's greatest mystery lies in what it conceals. While its outer layers are slowly eroding, its heart remains shrouded, impervious to prying telescopes. Infrared glimpses hint at colossal objects stirring within protostars so massive, their gravity warps the surrounding dust into swirling vortices. Some astronomers speculate these hidden giants could one day explode as supernova, their births and deaths playing out unseen behind the tower's veil. Others suggest even more exotic possibilities, black holes or rogue stars exiled to the nebula's depths and cloaked in perpetual night. The tower's most tantalizing feature, though, is its shadow play. As background starlight filters through its outermost filaments, the dust acts like a cosmic prism, bending and twisting the light into eerie, elongated streaks. These distortions aren't just artistic flourishes, they're clues. By mapping how the tower warps the light behind it, researchers can trace its magnetic fields, which appear to spiral around the structure like invisible support cables. This hidden scaffolding might explain how such a slender pillar withstands the chaos of its environment, its particles locked in a delicate dance between destruction and preservation. Standing at the crossroads of shadow and light, the Dark Tower is more than a celestial landmark. It's a laboratory for extremes where the universe tests the limits of gravity, magnetism, and radiation in a single, breathtaking experiment. And while its secrets remain locked away for now, every flicker of infrared light, every warp in the starlight around it, brings us closer to unraveling the story written in its dust, one that might rewrite our understanding of how the universe builds its most colossal structures in the dark. Drifting through the constellation Chameleon like a smudge of cosmic charcoal, the black cloud is more than just another dark nebula, it's a puzzle box of interstellar dust. Unlike the coarse, silicate-heavy grains found in most molecular clouds, this southern enigma harbors particles so peculiar, they've forced astronomers to rethink how stardust evolves in the galaxy's quietest corners. What sets this shadow apart isn't just its darkness, but the way it bends the rules of cosmic chemistry, offering a rare glimpse into the universe's most elusive building blocks. At first glance, the black cloud's dust seems unremarkable until you examine it through the eyes of infrared and radio telescopes. Spectroscopic analyses reveal carbon compounds unlike anything seen in nebulae like Taurus or Orion. Here, the dust grains are coated in a labyrinth of organic molecules, their surfaces pocked with microscopic pores that trap icy mantles of methanol and formaldehyde. These aren't the smooth, glassy particles typical of star-forming regions. They're cosmic sponges, their complex structures forged in the absence of nearby stars' disruptive radiation. Isolated in the chameleon void, far from the chaos of stellar nurseries, these grains have grown intricate over eons, their chemistry undisturbed by the shocks and winds that sculpt dust elsewhere. The real shock came when researchers measured the grains' light-scattering properties. While most dark nebulae absorb or reflect light predictably, the black cloud's particles do something bizarre. They polarize light asymmetrically, twisting it in ways that suggest their shapes are far from spherical. Some models propose they resemble jagged snowflakes or even tangled chains, their irregular forms defying the assumption that interstellar dust homogenizes over time. This anomaly hints at a hidden diversity in cosmic dust's family tree, or one where environment, not just composition, dictates how particles evolve. Equally puzzling is what's missing. The cloud's dust contains surprisingly little iron or silicon, elements typically abundant in similar nebulae. One theory suggests these heavier atoms have locked into complex organics, creating molecules too large to detect with current instruments. Another posits that the cloud's extreme cold, just 8 degrees above absolute zero, has allowed carbon monoxide and other volatiles to freeze onto grain surfaces, masking the signatures of heavier elements. Either way, the black cloud's dust behaves more like the primordial stuff thought to exist in the early universe, a relic preserved by chameleon stillness. What makes this nebula a Rosetta Stone for astronomers isn't just its oddities, but what they imply about the galaxy's life cycle. In turbulent regions, dust grains collide violently, shattering into simpler forms. Here, they've grown delicate, their fragile architectures intact. Some scientists speculate such particles could be the hidden carriers of probiotic molecules, their porous structures acting as safe havens for chemistry that might one day seed life. Others see them as time capsules, preserving a record of the interstellar medium before stars rewrote its rules. The black cloud's greatest lesson might be about perspective. We often assume darkness is passive, an absence waiting to be filled. But this nebula's dust is an active participant, its peculiarities sculpted by eons of quiet negotiation with the void. Every anomalous reading, every twisted photon tells a story, not just about how dust hides the light, but how it remembers the galaxy's untold histories. The Elephant Trunk Nebula in IC 1396 might steal attention with its radiant edges, but the real intrigue lies in its shadowy heart, a dense column of gas and dust so resilient it survived eons of stellar bombardment. While the surrounding emission nebula blazes with the blue-white fury of young, massive stars, the trunk's core remains stubbornly opaque, a fortress of darkness defying the very forces that sculpted its iconic silhouette. This isn't just a static sculpture, it's a cosmic battleground where gravity, radiation, and magnetism clash in slow motion, and the trunk's resistance to erosion holds clues to some of the universe's most delicate balances. Peering into the trunk's shadowy interior reveals a structure far more complex than its graceful curves suggest. radio telescopes pierce through its outer layers, uncovering a labyrinth of subfilaments twisting tendrils of molecular hydrogen and carbon monoxide woven together like a celestial basket. These strands aren't just passively drifting, they're under tension, stretched by the competing pulls of gravity and the stellar winds from HD 206267, the massive star responsible for IC 1396's glow. Normally, such intense radiation would shred a cloud like this within millennia, yet the trunk endures. The secret lies in its layered defenses. The outermost dust grains are sacrificed to the stellar onslaught, eroding gradually while shielding the denser material deeper within. It's a sacrificial buffer, like bark protecting a tree's heartwood from fire. But erosion resistance isn't just about density. The trunk's spine is reinforced by magnetic fields, invisible threads that channel and redirect destructive energy. Observations from the James Webb Space Telescope show these fields align along the trunk's length, creating a natural armor that prevents the cloud from fragmenting. Imagine a river of gas flowing through a canyon of magnetic force. While the edges fray, the core holds firm. Even more astonishing are the chemical quirks at play. The trunk's dust grains are rich in polycyclic aromatic hydrocarbons, organic molecules that absorb ultraviolet radiation and re-emit it as harmless infrared heat. This molecular sunscreen allows the nebula's innermost sanctuaries to stay cold and stable, even as the surface roils under stellar fury. Deep within this dark refuge, something else stirs. Infrared surveys reveal half a dozen protostars buried in the trunk's depths, their faint glow barely detectable through the surrounding murk. These infant stars are growing in an environment unlike the typical stellar nursery, shielded from radiation, their maturation slowed by the trunk's insulating embrace. Some astronomers speculate this could lead to unusual stellar properties, perhaps even affecting the planets that might one day form around them. It's a reminder that darkness isn't just empty space. It's an incubator capable of altering the very rules of star formation. The elephant trunk's greatest lesson might be about persistence. While the glowing nebula around it dazzles with short-lived brilliance, this dark column exemplifies the universe's quieter, more enduring forces. Every grain of dust that withstands destruction, every magnetic field line that holds firm, whispers a story about how delicate structures survive in a cosmos bent on tearing them apart. And as we unravel these secrets, we're not just studying a nebula, we're deciphering the hidden resilience woven into the fabric of space itself. The dark river in Ophiuchus isn't just a shadow, it's a cosmic highway, a sinuous thread of dust that winds through the constellation like a serpent slithering between stars. Stretching nearly 20 light-years, this enigmatic filament connects larger nebulae like Barnard's E and the Pipe Nebula, acting as a bridge between regions of star formation and interstellar voids. Unlike isolated dark clouds, the dark river thrives on connection, its tendrils weaving through space with an elegance that belies the violent forces shaping it. What makes this structure so captivating is its persistence. Interstellar space is a chaotic environment where shockwaves from supernova and stellar winds constantly tear clouds apart. Yet the dark river endures, its delicate filaments resisting dispersal for reasons that still puzzle astronomers. Part of the answer lies in its unique balance of forces. The river's dust grains are magnetically aligned, their microscopic shapes stretching along invisible field lines like iron filings around a bar magnet. These fields act as cosmic guide rails, stabilizing the filament against turbulence while allowing it to flex and ripple under external pressures. But magnetism isn't the whole story. The river's density fluctuates like a meandering stream, with dense knots of gas interrupting its flow. These knots are gravitational anchors, regions where material has pooled just enough to exert a pull on the surrounding dust. Radio telescope observations reveal carbon monoxide molecules vibrating within them, betraying the subtle tugs of nascent protostars, objects so young they haven't yet begun to shine. It's a cosmic balancing act. Too much mass and the knots would collapse into stars, too little and the river would fray into nothingness. The river's most striking feature might be its role as a conveyor belt. Spectroscopic studies show it's channeling material from the denser Barnard's E-complex toward the sparser Pipe Nebula, redistributing the ingredients for future star formation. This isn't a passive drift. The dust moves with purpose, guided by pressure gradients and magnetic drag. Some researchers compare it to a galactic circulatory system, with the river as a vein transporting raw matter to where it's needed most. Yet for all its order, the dark river isn't static. Infrared surveys catch flickers of change filaments splitting, knots brightening, and sections thinning as radiation from distant stars slowly erodes them. These subtle shifts hint at a deeper truth. Dark nebulae aren't frozen sculptures but dynamic ecosystems, where even the faintest shadows pulse with hidden activity. Every grain of dust here tells a story of resilience, a testament to how the universe weaves darkness into its grand design. Standing at the intersection of chaos and connection, the dark river challenges our assumptions about solitude in space. It's proof that even the most fleeting shadows can shape the galaxy, not by blazing brightly, but by flowing quietly, carrying the future in their currents. LDN 988 shouldn't be this warm. At first glance, this heart-shaped dark nebula in Cygnus looks like any other cosmic shadow, a cold, silent void where starlight goes to die. But train an infrared telescope on its core and the illusion shatters. Deep within its Inkai folds, subtle heat signatures pulse like a faint heartbeat, betraying activity where none should exist. This isn't just a passive cloud, it's a cosmic paradox, a dark nebula radiating warmth in the absence of visible stars. The discovery has astronomers scrambling for explanations, because LDN 988's hidden glow challenges everything we thought we knew about how these structures behave. The mystery begins with the nebula's isolation. Most infrared, bright, dark nebulae owe their warmth to embedded protostars' young suns heating their dusty cradles from within. Yet LDN 988's thermal fingerprints don't match that pattern. James Webb's mid-infrared instruments reveal a diffuse, uneven warmth spread across its entire heart-shaped structure, rather than concentrated hotspots. It's as if the nebula itself is generating heat, not just hiding it. One leading theory points to an unlikely culprit, interstellar lightning. As dust grains collide in the nebula's densest regions, they may build up static charges that discharge in massive, invisible arcs, a phenomenon observed in other molecular clouds. These discharges could heat surrounding gas, creating the faint infrared halo. But there's a twist. Spectroscopy uncovers another anomaly. Unusually high concentrations of hydrogen deuteride, a rare molecule that forms in extreme cold. If the nebula were truly warming from within, this fragile compound should have broken apart. The contradiction suggests LDN 988 might be caught in a delicate balancing act, its outer layers absorbing ambient radiation from distant stars, while its shielded interior remains frigid. This would make it a cosmic thermos, trapping heat in unexpected ways. The most tantalizing clue comes from the nebula's shape itself. That iconic heart isn't static. High-resolution radio maps show its edges rippling with supersonic gas flows. Some researchers speculate these motions generate friction, converting kinetic energy into heat like hands rubbing together in the dark. Others propose a more exotic explanation, decaying dark matter particles, their collisions releasing minuscule bursts of energy as they interact with the nebula's hydrogen. While far-fetched, the idea can't yet be ruled out. LDN 988 sits along a line of sight rich with gamma-ray anomalies, hinting at unseen particle physics at work. What makes this shadowy heart so compelling isn't just the puzzle of its warmth, but what it reveals about dark nebulae's hidden lives. We've long assumed these clouds are simple, passive things, celestial stage curtains waiting to be pulled aside. LDN 988 proves otherwise. Even in the deepest darkness, energy flows, transforms, and lingers in ways we're only beginning to fathom. Every flicker of infrared light from its depths whispers a challenge. The universe's quietest corners might be its most inventive, turning the void itself into a canvas for unseen physics. The Ghost Nebula doesn't just haunt the constellation Cepheus with its ethereal glow, it conceals a far stranger darkness beneath its shimmering veil. While Hubble's famous portraits showcase delicate tendrils of ionized gas, the nebula's true intrigue lies in the shadowy webs woven between them, filaments of dust so dense they swallow the very light that gives the ghost its name. This interplay between brilliance and obscurity isn't just poetic contrast, it's a cosmic physics experiment playing out in real time, revealing how photons wrestle with the universe's most light-hungry particles. At the heart of this dance is an anomaly called extinction, where dust doesn't merely dim starlight but alters its essence. The ghost's darkest tendrils exhibit extreme selective absorption, acting like a celestial color filter. Blue wavelengths, energetic and short, are the first to vanish, scattered into oblivion by fine carbon grains no larger than cigarette smoke particles. Redder light persists longer, penetrating deeper before succumbing, an effect that paints the nebula's edges with an eerie crimson blush. Yet in the densest knots, even infrared eyes like James Webb's struggle to see through. These regions achieve near-total opacity, their dust stacks layered like a million sheets of blackened glass. What makes the ghost's veil exceptional isn't just its darkness but its structure. Unlike the chaotic dust clouds of Orion, this nebula's shadowy components form geometric patterns, hexagonal cells, and near-parallel ribbons that resemble cracked ice under a microscope. Radio interferometry reveals why. Supersonic shockwaves from nearby stellar winds have compressed the dust into crystalline-like arrangements, with magnetic fields combing particles into orderly ranks. The result is a natural diffraction grating, bending light in ways that create the nebula's signature glow even as its darkest folds remain impenetrable. The nebula's piece de resistance, its dark halos are thin, soot-like bands encircling each glowing filament. These aren't shadows in the traditional sense, but denser accumulations of graphite and silicon carbide grains that have settled like sediment in cosmic eddies. Their presence betrays the ghost's turbulent history. Stellar winds have sculpted the visible gas while leaving heavier dust behind, creating a layered effect akin to ink dropped into water. For astronomers, this layered darkness is a gold mine. By measuring how the ghost's dust reddens and polarizes background starlight, they've uncovered clues about the interstellar medium's evolution. Some grains here bear isotopic signatures found only in meteorites, suggesting they predate our solar system. Others show crystalline structures thought impossible in cold space, hinting at fleeting encounters with ancient supernova heat. Every photon that fails to escape the ghost's veil carries a story, not just of obstruction, but of the intricate processes that turn stardust into the building blocks of worlds. The ultimate irony, this nebula's darkness isn't empty. It's a reservoir hoarding material until the next stellar generation awakens. Hidden within those lightless folds, gravity is already whispering, clumping dust into cores that may one day flare to life, trading shadow for brilliance. The ghost's true haunting lies not in what it hides, but in what it's preparing to reveal. The Rho Ophiuchi complex dazzles with its famous blues and golds, a celestial watercolor of reflection and emission nebulae glowing under the light of young, hot stars. But beneath this radiant spectacle lies an overlooked world of shadows, where dark nebulae weave through the region like ink spilled across a masterpiece. These obscuring clouds aren't just passive voids, they're active participants in one of the galaxy's most chemically rich environments, shaping the complex's evolution in ways light alone cannot. Take Barnard 44, a serpentine dark nebula slithering between Rho Ophiuchi's brightest regions. While its neighboring clouds blaze with scattered starlight, Barnard 44 absorbs with equal intensity, its dust grains growing fat on stolen photons. Yet this darkness is far from sterile. Radio telescopes reveal a bustling chemical factory within, where temperatures hover near absolute zero and atoms bond in ways impossible under warmer, brighter conditions. Here, carbon monoxide freezes into icy mantles around silicate grains, while hydrogen molecules rarely seen elsewhere cling to their surfaces like dew. These ices aren't just frozen relics, they're catalysts providing sticky landing pads for reactive molecules to meet and merge. The magic happens where light and darkness collide. At the edges of these dark nebulae, ultraviolet radiation from nearby stars like Antares and Sigma Scorpii drills into the murk, creating photodissociation regions, thin, hyperactive zones where chemistry explodes. Imagine a cosmic shoreline where the waves of starlight crash against the cliffs of dust, churning out complex organics like formaldehyde and methanol. These molecules don't survive long in the open, but within the dark nebula's sheltered pockets, they accumulate into reservoirs of prebiotic material. Some researchers believe these shadowed caches could eventually seed planets with the ingredients for life, delivered by comets born from the nebula's icy depths. What's truly astonishing is how these dark regions regulate star formation across the entire complex. While Rho Ophiuchus' glowing clouds host brilliant young stars, their dark counterparts act as gravitational anchors, their dense cores resisting collapse just enough to stagger stellar births over millions of years. Without this balancing act, the region might have exhausted its gas in a single burst of star formation, leaving behind a short-lived cluster instead of the sustained nursery we see today. The dark nebulae's resistance creates a celestial rhythm, slowing the symphony to a tempo that allows multiple generations of stars and possibly planets to emerge. Even their structure defies expectations. Unlike the chaotic filaments of Orion's dark clouds, Rho Ophiuchus' shadows exhibit eerie regularity, their tendrils aligned along magnetic field lines like iron filings. This organization suggests an unseen hand guiding the chaos, a magnetic scaffold that shapes both the darkness and the light. Some filaments appear braided, their strands twisted by passing shock waves from ancient supernova, while others stretch taut as bowstrings, vibrating with subsonic waves that may one day trigger new rounds of star birth. The ultimate paradox of these dark nebulae lies in their warmth. While their cores remain frigid, their outer layers emit faint infrared glows, betraying the presence of nanoscale diamonds and other exotic carbon crystals forged in stellar atmospheres and blasted into space by dying stars. These tiny gemstones, no larger than a virus, absorb starlight and irradiate it as heat, creating a thermal buffer that shields the delicate chemistry within. It's a reminder that even in the deepest cosmic shadows, there's hidden brilliance waiting just beyond sight to rewrite what we know about the universe's darkest corners. LDN 1774 isn't just another dark nebula. It's a cosmic recluse, a vast expanse of dust and gas that has stubbornly refused to birth stars for millions of years. Floating in relative isolation within the constellation Scorpius, this silent void defies the frenetic energy of typical star-forming regions. While neighboring nebulae blaze with newborn suns, LDN 1774 lingers in a state of suspended animation, its frigid interior untouched by the gravitational whispers that typically trigger stellar ignition. The question isn't just why this cloud remains dormant. It's how such pristine inactivity can even exist in a universe teeming with cosmic chaos. Peering into its depths reveals a paradox. At first glance, LDN 1774 appears ripe for collapse. Its core densities clock in at thousands of molecules per cubic centimeter, more than enough raw material to forge multiple stars. Yet infrared telescopes detect no telltale heat signatures of protostars, no flickering embers buried in the dark. Instead, the nebula's dust grains drift in eerie equilibrium, their collective mass held in check by forces we're only beginning to understand. One clue lies in the cloud's extreme cold. With temperatures hovering just 8 degrees above absolute zero, the thermal energy needed to jostle molecules into gravitational collapse simply isn't there. It's a cosmic deep freeze where even the faintest whisper of motion stalls, but cold alone doesn't explain the full story. LDN 1774's isolation plays a starring role. Unlike nebulae nestled in bustling galactic arms, this cloud drifts through a quieter interlude of space, far from the shockwaves of supernova or the gravitational nudges of passing stars. Without these external triggers, its gas remains eerily serene, a placid pool where ripples of collapse never form. Radio observations add another layer. The nebula's magnetic fields are unusually coherent, their invisible threads knitting the cloud into a stable tapestry. Imagine a spiderweb stretched taut, each silken strand resisting gravity's pull with microscopic precision. That's the delicate balance at play here, where magnetism and quietude conspire to keep star formation at bay. The most tantalizing hint comes from chemistry. LDN 1774's dust grains are coated in exotic ices, methanol, formaldehyde, and even traces of acetaldehyde compounds that act like molecular shock absorbers. When gas particles collide, these icy mantles convert kinetic energy into subtle vibrations, dissipating the heat that might otherwise seed instability. It's a self-regulating system where the nebula's own chemistry enforces its silence. Some researchers speculate this could be a galactic preservation tactic, a way to hoard raw materials until conditions are just right for efficient star birth. Others wonder if we're witnessing a rare cosmic hiccup, a cloud that missed its chance to shine. What makes LDN 1774 so compelling isn't just its refusal to conform, but what it reveals about the universe's quieter rhythms. While glowing nebulae dominate our telescopes, this shadowy holdout reminds us that darkness has its own purpose. Every molecule preserved here, every gravitational sigh suppressed, hints at a grander timeline, one where patience outweighs pyrotechnics and where some clouds wait as if knowing their turn will come. For now, the void keeps its secrets, leaving us to ponder the delicate equations that balance silence against creation. The Veil Nebula dazzles with its ghostly filaments, delicate strands of ionized gas glowing in the aftermath of a star's violent death. But just beyond this radiant wreckage, darkness lingers thick, brooding clouds of dust and gas that refuse to be illuminated. These shadowy counterparts, like Barnard 86 and LDN 1246, tell a parallel story, one where the same cosmic catastrophe that birthed the Veil's brilliance also sculpted these enigmatic voids. Supernova remnants and dark nebulae might seem like opposites, but they're locked in an intricate dance. When the shockwave from the Veil's progenitor star exploded outward millennia ago, it didn't just energize the surrounding gas, it slammed into nearby molecular clouds, compressing their already dense material into even tighter knots. Some regions collapsed under the pressure, sparking new star formation. Others, like Barnard 86, resisted, their dust grains absorbing the shock's energy without yielding. The result, a patchwork of light and shadow where destruction and creation blur together. Radio observations reveal the hidden mechanics at work. The Veil's shock front didn't merely plow through these dark clouds, it molded them. In LDN 1246, the blast sculpted wispy tendrils into sharp, comet-like shapes, their tapered ends pointing back toward the supernova like cosmic weather vanes. Magnetic fields trapped within the nebula's dust aligned with the shockwave's passage, creating eerily uniform striations that resemble tree rings, each layer marking a pulse of energy from the ancient explosion. But the real surprise lies in chemistry. Where the Veil's filaments glow with ionized oxygen and sulfur, its dark counterparts harbor molecules forged in the chaos. Spectroscopy uncovers ethanol, vinyl alcohol, and even glycolaldehyde, a simple sugar clinging to dust grains in these shadows. These compounds shouldn't survive a supernova's fury, yet here they thrive, shielded within the densest cores. It's a paradox. The same event that annihilated a star also created sheltered pockets where life's precursors could emerge unscathed. The most striking contrast is time. While the veil's glowing filaments fade by the millennia, their dark neighbors operate on a far slower clock. The supernova's shockwave may have jump-started changes in these clouds, but their evolution unfolds over millions of years. Some may one day birth stars, their delayed ignition a testament to the long tail of cosmic cause and effect. Others will linger as silent monuments, their dust whispering stories of violence absorbed and transformed. Standing at the boundary between the veil's radiance and these shadowed realms, we're reminded that destruction and darkness aren't in points, they're phases in an unending cycle. Every photon the veil emits finds its counterpoint in the light these dark nebulae withhold, a duality as old as the stars themselves. The California Nebula dazzles with its pink and crimson glow, a radiant expanse of hydrogen gas energized by the fierce blue star Xi Persei. But behind this luminous spectacle lies a hidden world, shadows so deep they vanish entirely from optical telescopes. These aren't voids. They're dense molecular clouds weaving through the nebula like black velvet ribbons, their presence revealed only when infrared and radio telescopes peel back the glowing facade. What makes these dark regions extraordinary is their defiance. The California Nebula's name evokes sunlit coasts, yet its obscuring dust clouds thrive in the same radiation that paints its brighter counterparts. While ultraviolet light from Xi Persei ionizes surrounding hydrogen into glowing plasma, these shadowy filaments absorb that energy instead, converting it into heat that warms their frigid interiors just enough to trigger unique chemistry. Deep within their folds, carbon chains and icy organic molecules flourish, compounds that would shatter under direct starlight. It's a paradox. The same radiation creating the nebula's brilliance also fosters its darkest corners. The contrast isn't just aesthetic, it's evolutionary. Near the nebula's Pacific coast, where dark and light regions collide, astronomers have spotted a phenomenon called radiative implosion. Here, the pressure of UV radiation squeezes dark cloud edges, accelerating their collapse into star-forming cores. One such knot, nicknamed the shadow core, shows infrared flickers of a protostar igniting under this cosmic vise grip. Unlike typical stellar births driven by gravity alone, this one owes its existence to the very forces trying to erode it, a celestial game of pressure and resistance where darkness fights back. Yet not all dark zones succumb. The nebula's most resilient shadow, Barnard 5, stretches like an ink blot across the Gulf of California region. Its dust grains are coated in magnesium silicates and graphite, a combination that reflects rather than absorbs UV light, acting like a cosmic sunscreen. This rare chemistry renders it nearly immune to erosion, allowing it to persist while neighboring clouds dissolve. Inside, temperatures hover near absolute zero, preserving primordial ices and gases untouched since the nebula's formation. The most haunting feature, these dark clouds sculpt the light around them. As Xi Persei's photons skim their edges, they cast towering, light shadows, ghostly pillars where radiation carves valleys into the glowing gas. The result is a nebula within a nebula, where darkness isn't passive but an active sculptor, shaping the very brilliance it opposes. In the California Nebula, light and shadow aren't rivals. They're partners in a dance that's been unfolding for millennia, each giving the other its form and purpose. LDN 43 shouldn't exist in its current form, at least, not according to our understanding of how dark nebulae behave. Nicknamed the cosmic tadpole for its bizarre, elongated shape, this enigmatic cloud in Ophiuchus stretches like a comet's tail across 17 light-years of space, its bulbous head glowing faintly from within. That glow is the first clue this isn't an ordinary dark nebula. Most molecular clouds this dense swallow light whole, but LDN-43's core emits a soft, eerie luminescence, betraying the presence of a young star that somehow shines through what should be an impenetrable shroud of gas and dust. The star, officially named ERAS 1628 plus 439, isn't just peeking through, it's warping the entire nebula around it. While most protostars carve orderly cavities in their birth clouds, this one has stretched its surroundings into a teardrop, as if the nebula is being pulled apart by invisible hands. The culprit, radiation pressure. Unlike the gentle glow of older stars, newborn suns blast their surroundings with fierce ultraviolet light and stellar winds. Normally, these forces create symmetrical bubbles, but LDN-43's asymmetrical shape suggests something unusual is at work, perhaps a lopsided distribution of dust or an external magnetic field twisting the cloud like taffy. Then there's the tail. Most cometary nebulae form when radiation sculpts dust into streamlined shapes, but LDN-43's wispy appendage points in the wrong direction, not away from the star but perpendicular to it. Submillimeter telescopes reveal the answer. This isn't just a passive filament. It's a cosmic umbilical cord, a bridge of gas and dust connecting the nebula to a larger molecular cloud complex. The star's radiation hasn't severed this connection. Instead, fresh material may still be funneling through it, feeding the young star even as it tries to blow its cradle apart. The most baffling feature is the core's transparency. Dark nebulae this dense should block all visible light, yet ERAS 1628's glow pierces through like a flashlight behind frosted glass. High-resolution imaging uncovers the secret. LDN-43's dust grains are unusually small and evenly distributed, more like fine smoke than the chunky debris found in clouds like Barnard 68. These particles scatter blue light but allow red wavelengths to pass, creating the nebula's haunting amber glow. Why the dust is so finely milled remains a mystery. Some theorists suggest violent collisions between grains triggered by the star's turbulence. Others propose the nebula is young, its material not yet clumped into larger aggregates. What makes LDN-43 truly remarkable is its defiance of categories. It's not just a dark nebula or a stellar nursery, it's a dynamic battleground where a star's birth is actively reshaping the darkness that birthed it. Every strange curve, every unexpected glow, tells a story about how chaos and order collide in the cold reaches of space. And while we've unraveled parts of the puzzle, the cosmic tadpole keeps its deepest secrets hidden, for now, content to drift through the cosmos as one of astronomy's most elegant anomalies. Near the heart of our galaxy, where stars crowd together like fireflies in a jar, lies a cosmic paradox, a dark nebula so massive, it defies the laws of stellar birth. Known as the Brick, this fortress of gas and dust carries the unassuming designation G0.253 plus 0.016, but don't let the clinical name fool you. This isn't just another shadow in space, it's a relentless puzzle, a 200,000 solar mass behemoth squatting just 25 light-years from the supermassive black hole at the Milky Way's core. Under normal circumstances, a cloud this size should be a star factory, churning out suns by the hundreds. Yet the Brick remains eerily dormant, its depths untouched by stellar ignition, and that quiet defiance has astronomers questioning everything they know about how stars are born. What makes this cosmic enigma so baffling is its location. The galactic center is a maelstrom of gravitational forces, where tidal energies from the black hole and pressure from surrounding starlight should be shredding clouds like this apart, or crushing them into star-forming fury. Instead, the Brick stands firm, its structure unnervingly stable despite the chaos around it. Submillimeter telescopes reveal why this isn't some wispy molecular cloud. Its internal density is off the charts, with gas packed so tightly, even the far infrared light used to probe it struggles to escape. If you sliced into the Brick's heart, you'd find carbon monoxide, hydrogen cyanide, and other molecules frozen onto dust grains in thick, dirty ices. a chemical cocktail typically ripe for star formation. Yet radio surveys detect no protostars, no flickers of collapsing cores. It's as if the nebula has built a cosmic vault, locking away its potential behind walls of dust and physics we don't yet understand. One theory points to turbulence. The brick isn't a serene, isolated cloud. It's caught in a gravitational tug of war. Nearby stellar winds and magnetic fields churn its innards, creating supersonic gas motions that counteract gravity's pull. Imagine trying to light a candle in a hurricane. That's the challenge facing star formation here. But turbulence alone doesn't explain the full picture. The nebula's magnetic fields are 10 times stronger than those in quieter star-forming regions like Orion, creating an invisible scaffold that braces the cloud against collapse. It's like a skyscraper reinforced with steel beams, except in this case, the beams are threads of magnetism woven through every filament, resisting compression with silent ferocity. Then there's the wild card, external pressure. Most dark nebulae collapse under their own gravity, but the brick is being squeezed from all sides by the galactic center's extreme environment. Some scientists argue this pressure should accelerate star birth, yet the opposite seems true. High-resolution observations reveal the nebula's core is fragmented into thousands of tiny, stable knots, each massive enough to form a star but held in check by some unseen equilibrium. One provocative idea suggests these knots are trapped in a feedback loop, where the very heat generated by their slow contraction is enough to keep them from collapsing further. It's a cosmic catch-22, a balancing act so precise it's halted stellar birth in its tracks. The brick's greatest irony, its darkness might be protecting its future. By resisting premature collapse, this nebula could be hoarding material for a later, more spectacular burst of star formation, one that might one day flood the galactic center with massive, short-lived stars. Or perhaps it's destined to remain a silent sentinel, its secrets locked away until new telescopes or theories crack its code. Either way, this shadowy monolith forces us to confront the uncomfortable truth. Even in the brightest, most chaotic corners of the galaxy, darkness still writes the rules. And until we decode them, the brick will loom as a reminder of how much we have left to learn about the universe's quietest architects. From the Inkai perfection of Barnard 68 to the magnetic defiance of the Snake Nebula, these 25 dark nebulae have one thing in common: they refuse to play by the universe's expected rules. Each one bends our understanding of how stars form, how dust behaves, and even how darkness itself shapes the cosmos. Take the Pipe Nebula, a celestial measuring stick that keeps its distance a secret, or Lupus 3's stubborn dark cores where chemistry fights back against starlight. The Ghost Nebula weaves shadows into stained glass art, while the brick near our galaxy's heart hoards enough material to build hundreds of stars, yet mysteriously it doesn't. These aren't just cosmic oddities, they're boundary-pushing experiments written in dust and gravity, forcing us to question what we think we know. What makes these enigmas so thrilling isn't just their defiance, it's how they collaborate with the universe's grand design. The Coalsack proves darkness isn't empty, it's a nursery in disguise. The dark Doodad starless patience reveals a slower, quieter path to creation, while LDN 1774's chemical freeze hints at ingredients for life preserved in cosmic deep storage. And then there's the ink spot, so dense it warps our very perception of light. These shadows aren't passive, they're active players, sculpting starlight, birthing worlds, and guarding secrets we've only begun to decode. The truth is, dark nebulae are astronomy's ultimate paradox, simultaneously hiding the universe's workings and revealing them. Their silhouettes teach us about magnetism we can't see, turbulence we can't measure, and chemistry too delicate to survive the light. Every unanswered question, from the Snake Nebula's eerie rotation to the brick's starless silence, cracks open new possibilities. Maybe some of these cosmic riddles will unravel with the next generation of telescopes. Others might linger for centuries, reminding us that the universe's greatest stories are still written in darkness. So the next time you gaze at the night sky, remember between the stars, in the spaces where the Milky Way seems to fray, entire sagas are unfolding unseen. These 25 shadowy puzzles are just the beginning. What else might be hiding in the dark? Stay curious, because the universe's next revelation could be lurking in the very void we've overlooked. And when it emerges, you'll be among the first to know.